Hello everyone. In this video, we're going to learn how to compute the area inside of a polar curve. The actual derivation of the formula for this area is a little bit beyond the scope of what I want to go over now, but suffice it to say that you can come across this formula by using Riemann sums. What you'll find is that the area inside a polar curve given by r equals f of theta, from theta equals a to theta equals b, is given by the integral from a to b of r squared over 2. Let's go ahead and apply this formula to the example r equals sine of 2 theta, where theta goes from 0 to pi over 2. Recall that the graph of this function is a 4-petal rose, and we're going to compute the area of this top right petal here. To do that, we just apply the formula and get that the area is given by the integral from 0 to pi over 2 of sine squared of 2 theta over 2. To solve this integral, we use the power reducing formula and then plug in our bounds to find that the area is pi over 8. Next, let's do something a little bit more complicated. Let's find the area inside of the circle r equals 3 sine of theta, but outside the cardioid r equals 1 plus sine of theta. First, a good place to start is always by graphing the two curves. If we do that here, we get something that looks like this. And now we want to find the area inside the blue curve, but outside the red curve. To do that, we're going to need to know the bounds of the integral that we're going to set up, which are going to be these points of intersection right here. To find those intersections, we set the given equations equal to one another, and find that the solutions are theta equals pi over 6 and theta equals 5 pi over 6. There are actually infinitely many solutions to this equation, but we really only need to worry about angles from 0 to 2 pi. Now, to find the area between these two curves, we find the area inside the circle between these 2 points, which is given by this integral, and subtract off the area inside the cardioid, which is given by this integral. I won't go through all the computations now, because we're all pros at integrating by this point, but I encourage you to do them on your own. You should find that the area is equal to pi. Alright, so in that example, we had to find the points where those two curves intersected. It wasn't terribly hard in that case, but it turns out it can be very hard to find the points of intersection in general. This is why it's always important that you graph the curves. To demonstrate a case in which it's much harder, let's try to find the area inside of the 4-petal rose r equals cosine of 2 theta, and outside the circle r equals a half. Like we said, we always start by graphing the curves. When we do that, we find the curves look something like this. And now we want to find the area inside the blue curve, but outside the red curve. Notice that this area is split into 4 equal pieces. That'll come into play in a little bit. But first, let's try to find the points of intersection. We set the given equations equal to one another and get cosine of 2 theta is equal to a half. Now we can just start writing out angles in ascending order that give a cosine of a half and find that 2 theta can be equal to pi over 3, 5 pi over 3, 7 pi over 3, 11 pi over 3, 13 pi over 3, and so on. Dividing by 2, we get that theta can be pi over 6, 5 pi over 6, 7 pi over 6, 11 pi over 6, 13 pi over 6, and so on. However, notice that only 4 of these angles are in between 0 and 2 pi, and then they start repeating. Recall that 13 pi over 6 is the same direction in polar coordinates as pi over 6. But we see in our graph that there are 8 points of intersection. So, where did the others go? It turns out we didn't account for all the points of intersection when we set the two equations equal to each other. To see why, notice that if we plug an angle into cosine of 2 theta and get out negative a half, then this point will also land on the circle. But we didn't consider this point when we set the two functions equal. Therefore, in this case, we also need to consider the solutions to the equation cosine of 2 theta equals minus a half. If we do this, we'll get 4 more angles, which turn out to be the ones we were missing before. So good, we found all the points of intersection. But now, how do we use them to set up an integral for the area that we want? Which intersection points do we need to choose as our bounds? It turns out the easiest way to compute this area is to just compute the area of one of the 4 identical regions that make up the entire area. Then we can multiply this by 4 to get the area of the whole thing. So now we just need to find one pair of intersection points that bounds one of the 4 regions. We have a lot of choices here, but we could see, for instance, that this point of intersection corresponds to theta equals pi over 6, and this one corresponds to theta equals 7 pi over 6. Therefore, to find the area of this left region, we take the integral from 5 pi over 6 to 7 pi over 6 of cosine of 2 theta squared over 2, and subtract off the integral from 5 pi over 6 to 7 pi over 6 of 1/2 squared over 2. Computing this integral, we find that the area of one of the regions is 1 over 48 times 3 square root of 3 minus 2 pi. Finally, we multiply this by 4 to find that the area of the entire region is 1/12 times 3 square root of 3 minus 2 pi.